Hello folks, in this video we're going to talk about electronegativity and polarity. In our last video we looked at electron distribution and how this impacted the molecular structure in 3 dimensions. This structure in 3 dimensions affects the charge distribution of the molecule, and that charge distribution has a significant impact on the physical and chemical properties of those molecules. So in this video we're going to take a look at charge distribution and how the different atoms within the molecule can affect that charge distribution. So we'll start out by just reviewing what we learned in the last video about 3-dimensional structures for simple systems. And then we're going to introduce the concept of electronegativity, which is a property of atoms which is key to understanding how the distribution of charge is affected within a bond. Then we're going to look at how that bond distribution affects the overall polarity or charge distribution of the molecule, introducing the concepts of polar and nonpolar, which we have talked about briefly in the past. Finally, ending up with a discussion of hydrogen bonds, which are special types of bonds that make water so very, very important and significant for life. All right, so here are some of the common molecular geometries that we looked at in the last video for different arrangements and numbers of electron groups around the central atom. I won't go through these piece by piece, only to note that it is the number of electron groups around the central atom that affects the arrangement of atoms around it, because we will be looking specifically at linear molecules like carbon dioxide and bent molecules like H2O and what that means with regard to charge distribution and polarity within those molecules. Okay, so we first introduced this property of electronegativity. Electronegativity represents the tendency of an atom to attract electrons within a bond. All right, so we're not talking about ionic materials here. We're talking about a covalent bond with shared electrons, but those electrons may not be shared evenly. Some atoms have a stronger pull on electrons and cause a charge distribution to shift toward those atoms which are more electronegative. So the more electronegative atoms will pull electrons toward them in a way that changes or gives us what we call a polar bond, so that there's a charge distribution toward the more electronegative one. Let me give you an obvious example. We're going to look at 3-dimensional models again in another video that goes through this in more detail. But for example, hydrogen fluoride. Now, we'll note trends in electronegativity within the periodic table in a few minutes, but I will point out that fluorine is the most electronegative element in the periodic table. That means within a covalent bond, it has the strongest pull of electrons toward it than any other atom in the periodic table. So what happens in this shared pair of electrons that we have here in the hydrogen fluoride molecule, fluorine is pulling electrons toward it and away from the hydrogen. So we're going to get an overall electron distribution, which if I can draw a simple shape here, we're going to see that the electrons are going to be, in fact, that electron density cloud around the atoms is going to be pulled toward the fluorine. So it's going to have a greater density of electrons around the fluorine than around the hydrogen because of its high electronegativity. Now, again, this is not a full ionic situation. So it's not stealing an electron from the hydrogen to become negatively charged, but it's pulling electrons, it's shifting the electrons in the bond toward it, such that while it doesn't have a full negative charge, we say it has a partial negative charge. All right, so it's not a -1 like a fluoride ion would be, but it's a partial negative charge, and we just represent that like that. And that means that hydrogen has a partial positive charge because they have to balance out. Overall, we have a polar bond, a polar covalent bond, because we've got an unequal sharing of the electrons within that bond. And in this molecule, what we have is a shift of electron density toward one side of the molecule, which is partially negative, and the other side of the molecule is partially positive. And in that situation, we say the molecule is polar. And again, we'll be looking at more detail and larger molecules here in this video, and then actually in a subsequent one, which is looking more at the three-dimensional structure of these systems. So how do we know which elements are having the strongest pull? I've mentioned that fluorine is the most electronegative element in the periodic table. There is a trend, and as you might suspect, it's the right side of the periodic table, the nonmetals, which have a tendency to gain electrons in ionic situations, which are also the most electronegative. Okay, so let's take a look. Here's a periodic table, and it shows our trend in the periodic table. Now I'm going to pause here because you may hear a dog barking in the background, but I'll be back in a minute. Okay, I'm back. So here's the periodic table, and you'll notice the little purple arrow here in the table, which shows the trend toward increasing electronegativity. So basically, what we're talking about, moving to the right and up gives the most electronegative element. So again, we'll see fluorine here, as we mentioned, is the most electronegative element in the periodic table. All right, so the higher it is in the periodic table, and the farther to the right it is in the periodic table, the more electronegative. And the reason for that is, to the right we have, of course, nonmetals, which have a tendency to attract electrons. So we'll note that property. But also it has to do with atomic size. As we go up the periodic table, the size of the atoms decreases. So the smaller, more compact atoms have a stronger attraction for electrons because simply they get closer to the positively charged nucleus. I hope that makes sense. So we see this trend as you move to the right and up, we're going to have an increased electronegativity. And again, fluorine is the greatest electronegativity. Now, you might ask, well, what about helium here? Because helium's right at the very top right corner. Why isn't helium the most electronegative element? It's a noble gas. And you remember from our previous discussion, it has a full shell of electrons. It doesn't want any more electrons. It's got enough electrons. It doesn't want to gain electrons. It doesn't want to lose electrons. So the noble gases have very, very low electronegativities because they just don't want electrons at all. So if we want to just kind of cross those guys out here, they don't have high electronegativities because they've got the full shell configurations and they don't need any more electrons. So again, fluorine is the most electronegative. We'll see oxygen over here. We'll talk about that in another video, but oxygen also is a very electronegative element. So fluorine is very electronegative as you go down a column. Chlorine's a very electronegative atom as well, but it's less electronegative than fluorine because it's larger, as we can see here. So as you go down, the electronegativity decreases. As you go to the right, it increases. Those are the general trends when we talk about the electronegativity. And so when we put these atoms together in molecules, we're balancing those electronegativities to see whether the bond, first of all, is polar, if the electrons are more attracted to one atom than the other, and then we add all the bonds together within the molecule to figure out what the overall charge distribution in the molecule is and whether the overall molecule is polar itself. All right, so here are just some simple examples. And again, I've got some three-dimensional cases in another video that we're looking at more closely. It's a range of molecules and sizes and types. But here's an example, some examples of some polar molecules, that is where the charge distribution is unbalanced. In this situation, we have, for example, here we've got water in this situation. And then the water has an unbalanced charge distribution because the molecule itself is not symmetrical. And so what we have is a situation where oxygen, again, is very electronegative. It's pulling electrons toward it. So we do have these polar covalent bonds in these cases that we see, and we'll write this as a little arrow pointing to the negative end, and we talked briefly about this in another video. And the positive at this one end represents that we've got a polar covalent bond with a partial positive at the hydrogens and partial negative at the oxygen. So the overall, when we add those together, it's like adding vectors together. If you remember how to do that, adding vectors together, overall, we get a charge distribution in the molecule that is partial negative at the top and partial positive at the bottom. So this situation where we've got a charge distribution which is not symmetrical, all right, where it's not balanced, that represents a polar molecule. Okay, and that impacts significantly the properties of that molecule. And we'll talk specifically about water in a couple minutes. A molecule like N2O, again, notice that the structure is not symmetrical. So if we don't have a symmetrical structure, we're not going to have a symmetrical charge distribution. And if we don't have a symmetrical charge distribution, the molecule is going to be polar. Why is this not a symmetrical structure? Because it's got two ends, nitrogens, on the left and the oxygen on the right. Now, if the structure was like this, which it's not, that would be symmetrical, okay? And that would give us a non-polar distribution, kind of like carbon dioxide down here at the bottom. That we'll see is because we got carbon on one side and oxygen on the other, that it's symmetrical, and this is a non-polar molecule, meaning the overall charge distribution is symmetrical, right? And again, even though oxygen is more electronegative than carbon, it's going to pull electrons toward it. It's like a little tug of war, where both oxygens are pulling electrons toward it from the carbon, but they're both pulling the same way. They both have the same electronegativity, so that means that nobody wins that tug of war, and the overall charge distribution is symmetrical. All right. Again, up here at the top, this little beastie here, in case you're interested, is formaldehyde. And again, the oxygen is very electronegative, and so we're going to see an overall charge distribution in this molecule that's oriented with a negative, with electrons distributed toward the oxygen, and so we're going to have a polar molecule. And by the way, these little arrows that I'm talking about here are called dipole moments. The dipole moment represents the degree and separation of charge within a molecule. A polar molecule has a non-zero dipole moment, while nonpolar molecules have a zero dipole moment. And again, if we look down here at the bottom, hydrocarbons in general, when we talk about hydrocarbons, molecules that just have carbon and hydrogen in them, those molecules tend to be nonpolar. Of course, when we talk about petroleum and petroleum products, those are largely based on hydrocarbons. They tend to be nonpolar. Oil and water don't mix. Why? Because water is polar and oil is nonpolar, and they don't interact well together as a result. So that shows you one of the ways in which the polarity of the molecule impacts its behavior. We see that polar and nonpolar don't mix, and that's why we see a separation. If you add oil and water together, you get a separation of the two layers of the liquids in that situation. So finally, on our last slide, we're going to talk about hydrogen bonding. This is a very special type of intermolecular interaction. And by intermolecular, what I mean is it's between molecules. This is a strong attraction between molecules. It's not a covalent bond, all right? It's not as strong as a bond within a molecule, but it is a strong interaction between molecules, which has a significant effect on the properties of molecules. Okay, so what we've got here in hydrogen bonding is a situation where, because of the very strong electronegativity of oxygen, we can see that the partial negative charge on the oxygen in one molecule can be attracted to the partial positive charge near the hydrogen end of another molecule. And that positive negative interaction is an attraction, right? It's a very strong attraction. Again, it's intermolecular, so it's not as strong as a covalent bond, but it is a very strong interaction between molecules. Now, typically, we like to say, and of course this is an average. On average, an individual water molecule will be hydrogen bound to 4 other molecules as depicted in this illustration. And you'll see here we've already talked about one. Here's another one with a hydrogen with a partial positive and a partial negative of an adjacent oxygen on another water molecule. Then we've got the oxygen itself attracted here, partial negative, partial positive. And we see 2 of these hydrogen bonds here. Why are there 2? Well, if you remember from a previous discussion, there were 2 non-bonding pairs of electrons on the oxygen atom within the H2 molecule. So because of that, we get 2 hydrogen bonds there as a result. Again, these are not as strong as covalent bonds, but they're pretty strong intermolecular interactions. And that attraction between molecules actually has an impact on properties. Now, typically, we're going to see hydrogen bonding. We're talking about water here in this example, but we see hydrogen bonding in a lot of molecules. Molecules that have oxygen, nitrogen, and fluorine, all extremely electronegative elements, have a tendency to hydrogen bond. Okay, so be on the lookout for that. If you're looking at molecules that have oxygen, nitrogen, and fluorine, hydrogen bonding will occur, and in those situations it does have an impact on some properties, like boiling points. Boiling point, remember, is the temperature at which a substance boils and goes from the liquid to the vapor phase. A strong attraction between the molecules is going to mean you need to put more energy into it to pull them apart when they go from the liquid to the vapor, right? So if we have that situation, if we think about water molecules here in the liquid phase and out here in the vapor phase, so here's our liquid, and here's our vapor. The water molecules within the liquid, in order to escape into the vapor, have to overcome interactions with other water molecules. And so energy has to be put into it to overcome those interactions to go from liquid to vapor. Hydrogen bonding holds them together more tightly, and therefore more energy is required in those circumstances to go from liquid to vapor. It means you need a higher temperature to boil. Water, for a molecule its size, and it's a relatively small molecule, has an anomalously high boiling point. Without hydrogen bonding, the boiling point would be much lower, and in fact, water would be a gas at normal temperatures and pressures. And we wouldn't exist if that wasn't the case. I mean, water has to be a liquid in order for us to exist. And so that hydrogen bonding is key to that, because the boiling point is well above, at 100 degrees Celsius, it's well above typical temperatures. So the high boiling point, it contributes to a high boiling point. We also know that the ice is less dense than the liquid, and so ice floats, right? That's very unusual. Most substances, the solid is more dense than the liquid, and the solid will sink. Ice floats. Why does ice float? The hydrogen bonding actually holds the molecules a little bit farther apart in the crystal, in the ice crystal. And that's because of the hydrogen bonding. So that means it's less dense because they're a little bit farther apart, and the less dense means it floats. Why is that important? Well, let me give you a really good example of this. Is if you think about a pond, for example, in the winter. When it gets really cold, ice forms on the top of the pond, right? And that ice stays on top of the pond. It doesn't sink, all right? If water ice was more dense than the liquid, it would sink. And what that means is if it really got cold, the entire pond would freeze, and that would mean all aquatic life would be killed, right? The fact that ice floats on top means that the aquatic life underneath survives, and the ice actually acts as an insulator from the very cold environment. So the ice floating allows aquatic life to exist. So that's really important. High heat capacities, we've already talked about the high heat capacities when we talked about thermal properties of systems. Water has a higher heat capacity than many substances, particularly substances its size. And that allows it to moderate temperatures because it has such a high heat capacity. It can take heat in without raising its temperature very much. So that moderation is actually key. So all of these, and there are many other factors that are affected by hydrogen bonding that are key to life. The DNA strands are held together by hydrogen bonds between the strands. Hydrogen bonding is everywhere. It's important in biology. It's important for our life. It's an intermolecular interaction due to electronegativities of the atoms and the polarities of these systems. I think that's pretty neat. I hope you do too. Let me know if you have any questions.